What are the properties of matrix multiplication? If the products and sums, if the product and sum are defined, then A, we're looking at if you're multiplying by a scalar, it doesn't matter if you're multiplying two matrices and you're multiplying one of them by a scalar, it doesn't matter when you do the scalar multiplication. That's what the first property tells us. Alpha multiplied by matrix A is then multiplied by the matrix B. It's the same as removing that scalar and multiplying the two matrices A and B and then multiplying by the scalar. Or you could leave the first matrix as it is and multiply the second matrix by the scalar alpha and then do the multiplication. It doesn't matter. B, the associative law. If you're multiplying three matrices, A, B, and C, it doesn't matter when you do the multiplication of two matrices, right? So in the first case, you can leave the first matrix as it is, multiply the second and the third, and then work out the product with matrix A multiplied by the product that you ended up with. It's the same as taking or multiplying the first two matrices and taking that result and multiplying by the third matrix. What I'm doing is I'm trying to verbalize it so you understand what the rule indicates. It's important to unpack what the symbols represent. See the distributive law. So this is, you got a matrix A and you want to multiply that by the sum of two matrices B and C. So you could multiply it like this. So it gives you AB plus AC. If the structure is in what's in the following line, where you've got the sum of two matrices and then you're multiplying that sum by a third matrix, which we're calling A in this case, right? It's the same as this, but remember you're multiplying from the left, right? So it's going to be BA. The order is important because matrix multiplication is not commutative, plus CA. For proofs, you must see example 4 and example 5 on pages 13, 14 of your notes. Right, the next question we look at, how can we write a system of linear equations in matrix form? We're going to do this by means of an example so that you understand what's going on. Example 3, write the following in matrix form. So here, the solution. For the matrix representation. Right? So you first, on the left-hand side, if you look at the equations, all your terms in x are one below the other, same for y and z. To the right of the equal to sign, you've got the constants. So the matrix, the equations are in standard form. What we do is we take the coefficient matrix from the left-hand side. That's going to be 1, -2, 3. That's from the first line, first equation. 3, 4, -2, 2, -3, 7. Right? And then we multiply that by the column matrix, which comprises of the variables x, y, and z. That's equal to, it has to equal to the constants that are in the right hand side. So the matrix of constants, that's -1, 1, 6. Right? If you multiply the matrix out on the left hand side, those two matrices on the left hand side, you will end up with a 3 by 1 matrix. And you'll see that the corresponding entries on the left hand side will equal to what's on the right hand side. So you really end up with those 3 equations. You need to do that so you understand what's going on. Like if you take the first row in the first matrix and the column matrix, it's going to give you x minus 2y plus 3z. And you'll see that that's equal to -1. You can do the same for working with the second row, so on. So here note that this first matrix, to get the matrix representation of the system of equations, you need to get the coefficient matrix. Right? That is multiplied by it's a column matrix of variables, right? X, Y, and Z. Then you've got over here the matrix of constants. Again, it's a column matrix. Right, so make sure you understand this. We will need this after we do the next section on inverses of matrices. It'll give us another way of solving systems of equations. So we're now on to page 4 of the lecture outline. And the first question that we are looking at is, what is an identity matrix? Right, so what is an identity matrix? Right, this is a square matrix which is square matrix satisfying the following conditions. 1, all entries on the main diagonal are 1 and all other entries are 0. So supposing right, you're looking for the identity matrix is labeled with a capital I, so the identity matrix of order 2 is going to have 2 rows and 2 columns. This is going to be it. In the main diagonal, your entries are going to be 1. All other entries will be 0. So this here is an identity matrix of order by 2, right? This one here is the identity matrix of order 3 by 3. So your identity matrix of order 3 by 3, in the main diagonal, the entries are going to be 1. All other entries will be 0. The next question that we look at, what are the properties of the identity matrix of order n by n? In other words, it has n rows and n columns. So one, your identity matrix of order n multiplied by the matrix A will give you the matrix A for any n by m matrix A, right? That's for the multiplication of matrices to exist. Number 2, the matrix B multiplied by the matrix, the identity matrix of order n by n, this would equal to the matrix B for any, now your matrix B will have to be of, say, m by n. The n will have to be fixed for the multiplication to exist, right? Then the third part, 3, the identity matrix of order n by n multiplied by the matrix A will equal to the matrix A multiplied by the identity matrix of order n by n, and that will equal to the matrix A for any square matrix A of size. In this case, it will have to be n by n, right? So if you're multiplying by an identity matrix, a given matrix by an identity matrix, right? And that given matrix is a square matrix. It doesn't matter which side you multiply by the identity matrix. Why? In this case, it's going to be commutative. You end up with the same matrix A in this case. Okay, we'll stop over here. Take care.